So hello everyone, we are learning the subject of electromagnetics and that too chapter of your the radiation, that is electromagnetic radiation. So today we will simplify the few numerical on the radiations or the electromagnetic radiations. So what is that numerical here? Find the radiation resistance of Hertzian dipole of a length lambda by 4, lambda by 60 and lambda by 80. In the theoretical part, we have studied about the Hertzian dipole, how we can write the expression for finding the electric as well as the magnetic field by considering the dipole in the Hertzian expression. Okay. So the dipole already we have studied. If you are considering the antenna and the source is there, then there will be the division of that length in the two portion, that is a d by 2 and the d by 2, that is L length is dividing in the two sections, and accordingly the signals will be passed from the upper and the lower, you can say, or the 2 points, you can say, for the first that is a d by 2 and for the second also for the d by 2 likewise. So here what is given, the length is given, that is nothing but the wavelength is given, lambda by 4, lambda by 60 and the lambda by 80, and we need to find the radiation resistance, which is denoted by R. So how we can start here? So we need to start by writing the expression, by writing this sentence, that is the radiation resistance, which is denoted by RR. You can also mention here the radiation resistance in bracket capital R small r bracket close of a Hertzian dipole of a length. So length will be here, that is a DL, that is nothing but the differential length is. So what is the formula? This is the derived expression of you from the theoretical point of view, or from the what we can say the scientist of your the Hudson and many more which we are going to use. So that is a derived expression. Directly we are using here this expression for simplifying the numericals. Okay, so for finding the radiation resistance, which will be the internal resistance placed. Okay, and we are interested to find out that internal resistance. So how it is possible to calculate? RR is equals to 80 pi square into bracket dl by lambda square. Okay, and we are aware from that in radiation resistance is measured in the Ohm, and dl is nothing but the differential length, lambda is nothing but the wavelength. So how we got this 80? That already we have derived these expressions. Okay, so this what is the unknown here? If you observe 80 will be as it is, pi square will be as it is. Here three parameters are given: lambda by 40, lambda by 60 and lambda by 80. So one by one, if we are going to substitute the value of your the dl, like if dl is equals to lambda by 41 time, if dl is equals to lambda by 61 time, and if dl is equals to lambda by 80, because the dipole of length is given. Okay, so these three things are given in each situation, in each section we need to calculate the RR, that is nothing but radiation resistance. So how it is possible? You just here substitute the value of your dl lambda by 40 here, and this 1 by lambda will be as it is. See, 1 by lambda will be as it is. We are substituting the value of your the dl, that is nothing but lambda by 40, lambda by 40. So what will happen? This lambda will cancel out, and 1 by 40 will be remain, and that to this bracket square. So you need to do for 40 square. Okay, so even after getting that 40 square, 80 divided by the term, okay, will come, and the pi square, if you are going to multiply and divide and all these things, you will get that radiation resistance is nothing but 0.493 ohm. For which case, when the lambda by 40 is there, that is a differential length is lambda by 40. Similarly, if you are going to change the differential length, that is nothing but your the again the lambda by 60. So in that case, you can say lambda by 60, just change the value. Here will be your the lambda by 60, 1 by lambda. Again the lambda will cancel out. 1 by 60 will be there, and here the bracket of square means 1 square divided by 60 square, like this. And you just 80 divided by that is 60 square, divide will be there, and multiply with the pi square. So you will get finally that is 0.219 ohm. 0.219 ohm. Again, if we are in the third case, if you are going to change the differential length, that is nothing but you are the lambda by 80. So that lambda by 80, where we are going to change that lambda by 80. We are changing that lambda by 80 at the place of your the dl. So again the dl will be lambda by 80. Okay, and this 1 by lambda will be as it is. Lambda will cancel out and 1 by 80 will be there, and that 1 by 80 is nothing but 1 by 80 square. So this you need to take outside, you need to divide, you need to multiply with the pi square. So then you will get again the third value, that is of radiation resistance is nothing but your the 0.123 ohm, which is measured in the ohm. So this way this numerical was related to finding the radiation resistance. If going to use the Hudson dipole expression, then only it is possible to simplify that radiation resistance. Go for the next one. Find the directivity of a current element, comma, find the directivity of the current element IDL. So what we need to find here, see, very in short, the question is in the single line. Find the directivity of the current element IDL. Nothing is mentioned here, which is whether we have only the unknown parameter we need to calculate, but what is there is not mentioned. So in such a case, so you can assume anything. Okay, you can assume it's no doubt at all. This numerical is related to the radiation. How you can find the this numerical is related to the radiation? Just because of this word, that is nothing but the directivity, that is nothing but the length of the particular direction. The length which is going at a particular direction is nothing but the directivity of that. And that we can measure for the antennas whenever we are having the transmitting and the receiving antennas, in which particular direction the antenna is placed. Accordingly, the directivity, the direction will go, and the radiation we can find easily. So in this way, the current which is flowing through that particular directivity or the direction, that current is nothing but I into dl. That we are interested to calculate. So here in this case, how we can determine the directivity D, that we will see here one by one. So the amplitude of electric field for the finding the current element is E is equals to, this is also the derived expression, so don't bother here, simply note down these formulas. So E is equals to I into dl sine theta divided by 4 pi epsilon 0 into omega r v0 square. So this is nothing but the expression of your the electric field intensity, okay, for finding of the directivity. So what is that? I dl sine theta divided by 4 pi epsilon 0 into omega divided by r v0 square. So here I into dl, or simply I is nothing but the current, dl is nothing but the differential length. Okay, sin theta and the cos theta totally depend upon how they are going to be placed. Okay, and if you want to find out, this omega is nothing but the angular frequency, r is nothing but the radius, and this is the velocity of propagation. Okay, in the yesterday case also we have found v0 is equals to 1 by root of mu 0 epsilon 0. In this way also you can find, but here is a v0 square, so directly you can take, instead of taking the squaring term and all, directly you can take as 1 by mu 0 epsilon 0, and these are two constants value, that is nothing but 4 pi into 10 raised to the power minus 7 and the 8.854 10 raised to the power minus 12. So these two constant values is substitute here. The radius we will find here. This 4 pi epsilon 0, again this is the constant value you can substitute here. Okay, so what is my omega is the 2 pi f, that is mentioned here 2 pi f. What is the ideal sine theta will be as it is. How I can find the omega 2 pi f? By substituting the value of the frequency. How I can find the v0? 1 by root of v0 epsilon 0. So you will be able to find here after substituting this value. So what will happen? Just omega, see here, ideal sine theta divided by 2r. Ideal, how we got this 2? This 2 pi f, 2 will be cut with the 4. 2, this 2 will be cut with the 4. That is nothing but this 2 and this 4. So here will be again the 2. Okay, so you can take here the 2. This pi will be cancelled out. Okay, and this epsilon 0 is here. Okay, epsilon 0 is here. So how you can take here? Now the 2 and this 2, you will get this 2r. Pi will be cancelled out. What is the remain? F will be remain in the numerator. I will be remaining in the numerator. Dl sine theta f. These two will be remaining in the what you can say numerator. Okay, divided by 2r will be as it is. And these two, that is nothing but the root of mu 0 epsilon 0 mu 0 because of the v0 square meter. Okay, so in this way we can find easily that is nothing but the intrinsic impedance instead of taking that in the multiplication. If you are going to take in the division form, so you will get as a root of mu 0 epsilon 0, that is nothing but the eta, and the lambda by this above formula v0 by f. So V0 by F is nothing but the lambda wavelength. These are the adjustment by which you can get easily, because just because V0 is 1 by root of so and so, and other parameter, this is in the denominator, how we can take this one. So these are the adjustment by which we can simplify the expression. You can solve this expression. Later on, what will happen if you are going to substitute the previous case? That is nothing but what will be my f by lambda, f will be as it is, v0 will be there, f into root of mu 0 epsilon 0. So in this way, the finally e will you get as a, after cutting and all, if you observe in the previous two, maybe the step will increase, one or two step will increase, you will get as e is equals to 60 pi I dl sin theta divided by lambda into r, divided by lambda into r. So the maximum radiation occurs at, so here how we can get, and because we know very well in the particular direction or the angle is changing or the sinusoidal waveform is there. So at every instant we are interested to find out the radiation just because that is traveling in the free space. So here the maximum radiation occur whenever you are having E max is equals to, or simply the theta will be equals to pi by 2. So how it is possible to get that expression? So E max is equals to 60 pi I dl divided by pi r. So now just substitute the value of what is it, theta is equals to pi by 2, or if you are having the pi by 2 at that time, you can substitute the value of the theta. That also possible. Okay. So the radiated power of the current element, that is here, we remember in the many of the textbook, maybe that is the PR. Okay, in the many of the textbook, that may be the PR. So here, instead of writing the PR, they are taken as here the W, that is nothing but the radiated power. Even though you are taking the PR, doesn't matter. You can take directly here the PR also, that is nothing but radiated power is equals to of the current element, radiated power of a current element is. So with respect to the current, we are interested to find out this radiated power, and we know whether the power is having a various formulas, just like your I square R and VI and the V square by R, likewise. You can now consider any one of the formula and you can write that expression. So in the previous case only you written that 80 pi square T dl. Okay. So with the help of that also, if you observe this previous slide now, just note. So here, where is that? See, this RR is nothing but the 80 pi square. Again, the DL by lambda. This is nothing but the radiated resistance. Because I square R term is also there. We remember I square R power P is equals to I square R. So at that time, you should remember what is my R. R is nothing but this entire term. You can consider even the E. If you are taking the E max or the E electric field, that time you need to consider this expression. So these are for remembrance how we are going to take this one, and you need to substitute the value. How I can find my the radiated power? If I'm going to assume, I'm assuming that my radiated power is nothing but 1 watt at the time. What is the possibilities? So if you are going to substitute the value here, we guess this I square term is there. So I'm going to take this I. Okay. If I'm going to take this I is equals to lambda by this square term. This is a without square sum. So you can take here the I is equals to lambda by root of 80, the 85, and that to di ampere. So this we are going to measure in terms of the ampere, that is nothing but the current. If you want to find out the E max, yeah. If you want to find out the voltage at a maximum, so that time also it is possible to measure that E max. Okay, and you can substitute and you can find here. So what is the value of your the lambda? What is the thing here? The 60 is nothing but this is the expression, direct expression whenever you are having the maximum electric field or the maximum radiation at a particular electric field. So that we have that expression. Okay, this expression. If you are going to keep the pi by 2, you can. Okay. So pi by 2 also you can substitute there also. So likewise, you need to substitute this 80 pi, then that d I by lambda square, this is the square root term. Then we are interested only the I, then you can take that I is equal to lambda of so and so appear. Then you can write the expression of E max, which is the previous, that is a 60. Okay, so this lambda, this root of 80, how we got it by substituting the value of the I, because I is here again, 60 pi IDL. So I substitute the value of I here, you will get the E max. Likewise, you can, what you can say, compare the expressions and you can substitute the value which is unknown and you can find the things. So maximum radiated intensity is given I. RI is nothing but maximum radiated, yeah, radiation intensity. Okay, R is a radiation and I is the intensity is given by I square E square max. Here again, the small is the radius and the E max is nothing but the maximum, what you can say, the electric field. Okay, maximum value of your electric field. So here R square is square divided by E. That's the step of expression is was also available in the uniform plane here also. So here the radius will be as it is. What is my E term? You just check here. That is the 60 R root of 80 degree. So this is the squaring term. So this root will be cancel out. 60 will be squaring this one. Okay. What is the remaining part here? How we got this 1 over 8 pi? That is eta. We know very well the value of eta. You can substitute either the 377 or the 120 pi. So likewise, you can substitute. You will get finally that is a radiation intensity. Ri is equals to 3 by 8 pi. Okay, 3 by 8 pi. So maximum directive gain, that is nothing but the GT. G is nothing but the gain, D is nothing but the directive. So maximum directive, max is nothing but the maximum directive gain. So that is denoted by D is a directive, G is the gain, and that to maximum. So GD max is equals to GD max is equals to 4 pi Ri divided by WR. 4 pi Ri divided by W. All the formulas which are mentioned here, you just keep in the box. So you will be easily simplify the numerical in future by changing the values. So 4 pi will be as it is. What is Ri? Ri is nothing but the 3 by 8 pi. 3 by 8 pi. Okay. 3 by 8 pi. So here again, this 3 by 8 pi will be cancelled out. Okay. Pi will be cancelled out. So in this way, you will get as a 3 by 2, that is nothing but the 1 by 8. 1 by 8. So this 1 by 8, that directive, oh, always remember the directivity can be measured in the dB. Okay, directive measured in the dB, either in terms of the gain of the current element or whatever it is. Once you got the answer, you need to convert into the what we can say the dB. Okay, you need to convert into the dB. So how it is possible to convert into the dB? D is a directivity, capital D, and we know very well that is equivalent to your the directive gain and maximum directive gain that we are having a 1.5. So how we can convert this maximum directive gain, that is a GD, maximum directive gain can be converted into the directive that is in the dB, that is a 10 log 10 of GD, 10 log 10 of GD. So that GT is nothing but 1.5. So if you do with the calculator, 10 log 10 of 1.5. 10 log 10 of 1.5 will be your 1.76 dB. 1.76 dB. 1.76 dB. Yes. So if you simplify the next numericals, see here, these previous one, 8.2 and 8.3 are connected to each other. How? Because they are find the directivity of the half wave dipole. So in the previous one, we have calculated find the directivity of the current element IDL. IDL. So if we want to find out for the particular dipole, so for that, this is the for the full dipole, you can say, for the entire length, you can say, for the entire dipole, you can say. But here, if we are interested for the half, definitely the expression somewhat will be changed in the numerical. Okay, and even the expression of the I, expression of your the power radiated, all these together will be changed. Okay, so how I can find my the maximum electric field in that particular half wave dipole, expression will be directly 60 I by R. R is the radius, I is the current. Okay, and how I got the 73? 73 is the because the derived expression for the eta. So here the power radiated power will be equals to eta I square, or simply if we are taking what we can say the radiated resistor, if you are taking power I square R, so that our internal resistance you can take as the 73. This is the assumed one, just because whenever you are taking for the half wave dipole, you can assume, definitely you can assume if you are having the half dipole. So in that particular case, so in this way, what will be the case for omega for the 1 watt? How we are getting this 1 watt? Again, here there is no as such watt is mentioned. In the previous case also not mentioned. So if you want to substitute to calculate this I, you need to assume that the radiated power is of a 1 watt. If it is 1 by 1 divided by the 73 will be there, that is I. So I will be equals to I square is here, but if you want to find the I is equals to 1 by root of 73. 1 by root of 73 you can find. So now next is nothing but if you are going to what you can say, if you are going to calculate directly I, you can, otherwise you can substitute in the Emacs. That is also possible. Only the unknown parameter is the radius. Now if you are going to substitute the value of Emacs 60 by R and the value of R is still unknown, but I you got that is nothing but 1 by root of 73. So now go for the next, that is the directivity gain, maximum directivity gain. For this half dipole is 4 pi Ri WR. What is Ri? Radiated intensity. 4 pi by omega. Omega is R is nothing but the radiated power. So you can substitute the value. Where is Ri? Radiated intensity can be calculated. We know very well R square, that is the radius, and E electric field square divided by eta 0, that is at free space, intrinsic impedance at a free space. So see here, R square, E square divided by eta 0, E square divided by eta 0. This value you can substitute for the Ri, because directly we are not having the value for R, we are not having the value of I. That's why we can substitute here the Ri. This R square, E square, and eta square. We can take directly for the character this Ri divided by this omega. You can take, okay. You can take for that one also. So in this way, what will happen? 4 pi will be as it is, R square will be as it is, E square will be as it is, eta 0 will be as it is. Okay. What about the for the omega? Omega values upper mentioned in terms of the Emacs. In terms of the Emacs, that also you can substitute the value for that current Emacs value in terms of the 60 and the current you calculated 1 by root of 73. Likewise, all the parameters which you have calculated related to the omega, related to the Emacs, you can substitute here. So finally, you will get as the directive gain, maximum directive gain is nothing but 1.644, 1.644. So if you don't want to convert that directivity, final directivity into the dV, then you can write same answer. If you want to convert, so what will happen? 10 log 10 of 1.644. 10 log 10 of 1.644. So this is also possibility to get that answer of your the directivity. But here the gain, directive gain is important. They are asking about the maximum directive gain, that is a GD max. So that also possible to calculate the D by referring this formula. Capital D in the dB, capital D in the dB is equals to 10 log 10 of 1.644. So next numerical is mentioned here in the bottom. Other than an antenna whose radiated resistance is 300 ohm. Radiated resistance is 300 ohm. Operates at a frequency of 1 gigahertz with a current of 3 ampere. Find the radiated power. See here, radiated power denoted by omega R, and the antenna resistance is having of a 300 ohm. Operates at a frequency of 1 gigahertz. Operates at a frequency of 1 gigahertz. Ampere is given 3 ampere, and we need to find out the radiated power. So radiated power, this is also the radiated power can be calculated I square R formula with the help of I square R formula. Radiated power also denoted by the PR or is equals to omega R, which is equals to I square RR. So I is nothing but the 3 ampere is given, RR is given 300 ohm. So in this way you will get the radiated power as 2700 watt, 2700 watt. So this is the radiated power. Now next is, what is the effective area of half wave dipole operating at a 500 megahertz? So what is the effective area? Effective area. The effective area means wherever you are having the antenna, okay, at that particular either the transmitting or the receiving antenna, from where the signals are going to be passed on that particular section of where the signals are going to be passed, surrounding of that signals is nothing but that particular is nothing but the effective area of that antenna, okay. Because there are various parameters related to this antenna, aperture antenna, effective antenna. So this is the theoretical part we will discuss later on. But for the numerical point of view, we remember this is a particular area which are at either the transmitting or receiving antennas, which we are interested to find out the signals, whether the signals is strong or the weak. How it is possible the effective area of that particular antenna can be calculated. AE is equals to lambda square by 4 pi GD. D is nothing but directive, G is nothing but the gain, and lambda is the wavelength, the A is nothing but the effective area. So substitute the value of the frequency here, F is equals to 500 megahertz. Why we are interested in find out the frequency? Just because of the lambda. Lambda is correlated with the frequency because F is equals to is inversely proportional to 1 by lambda, or lambda is equals to inversely proportional to 1 by frequency. Likewise, they are inversely proportional to each other. So once you got the frequency, definitely you can get the lambda just because of the formula of V0 by F. What is the V0 or a capital C? C is nothing but the velocity of the light. That is the 3 into 10 to the power 8 divided by F. C by F. Lambda is equals to C by F. So C is at 3 into 10 to the power 8 divided by F is nothing but 500 into 10 to the power 6. So in this way, if you are going to substitute this value, you will get lambda is 3 by 5. That is nothing but the 0.6 meter. 0.6 meter is nothing but the wavelength. 0.6 meter is nothing but the wavelength. Now go for the next. Similarly, in the same, we need to calculate the effective area. So directivity of the half wave dipole, that is the GD max. You can get D is equals to 1.644. So how you can get the E? That is lambda square. That is nothing but 0.6 square divided by 4 pi into 4 pi into what is GD? GD is nothing but 1.644. So substitute this value 0.6 square divided by 4 pi into 1.644. So in this way you will get effective area is nothing but 0.047 meters square measured in meters square. So area is measured in meter square 0.47. So now the similar question related to finding the effective area in the Hertzian dipole operating at a frequency of the 100 megahertz. So see here the only the frequency is changing and we need to find out the what you can say the effective area. So what is given in the numerical F is given F is equals to 100 megahertz. F is equals to 100 megahertz. So lambda can be calculated. Lambda is equals to C by F. So C 3 into 10 to the power 8. Your C by F. F is nothing but again the 100 megahertz. So in this way, it will be here the mega 10 to the power 6 and these two are 100. So here will be 10 to the power 8. Just because of that, just this to cancel out this 10 to the power 8, we have converted this 100 megahertz into the this 100 into 10 to the power 6. So here will be the 3 meter will be here the lambda, that is directivity of the Hertzian dipole is nothing but half of that because half dipole, Hertzian dipole is half of that previous one. So how we can find the effective area, that is lambda square, lambda square D divided by 4 pi. That's why we require the capital D, that is nothing but the directivity and which is nothing but the half of the wavelength. So that is nothing but 1.5. 1.5. So 3 square into 1.5 divided by 4 pi will be as it is. So if you multiply with this one, 3 square into 1.5 divided by 4 pi, so you will get 1.07 meter square. 1.07 meter square. 1.07 meter square. So next numerical is to calculate the time period, time taken by the wave to travel. So here an EM wave of 1 gigahertz is radiated by an antenna to cover a distance of over the 100 kilometer. Determine the time taken by the wave to travel the above distance. So electromagnetic wave is given having the frequency of 1 gigahertz, okay, and radiated by the antenna obviously to cover the distance of 100 kilometer. Determine the time taken means time required for what we can say time taken by the electromagnetic wave from the radiating from the antenna. So how it is possible the time taken by the electromagnetic wave is given as small d is equals to d by v0. What is d? D is nothing but the distance, v is the velocity of propagation. So what is the distance? That is 100 kilometers. So 100 as it is velocity of propagation is V0. So that we know very well. Again, we just substitute D. D value is nothing but 100 into 10 to the power 3. Kilohertz is mentioned. 100 kilometer. So 100 into 1000. Okay, divided by what is V0? 3 into 10 to the power 8. So likewise, this 5 and this 8. So you will be able to find 10 to the power 5 divided by 3 into 10 to the power 8 is nothing but 0.333 10 to the power minus 3. That is nothing but the what you can say millisecond. But that will be converted into the millisecond, but 0.33 if you are going to convert So this minus 3 and this minus 3 become as a minus cube second. So 3 microsecond, 333 microsecond. So in this way, we can calculate this in a simple way, the time taken by the wave, electromagnetic wave traveling in the field space. By knowing the frequency of radiated frequency through the antenna and other parameter, we can find. So with the help of that time required, the distance and the velocity of propagation is important. So we have calculated that is a 333 microsecond. So in this way, we have simplified the numerical on the basis of the radiation, electromagnetic radiations. So in this way, we have calculated the time period T. So we have simplified the field numerical on the basis of finding the radiated, what we can say, radiated power. We have calculated the effective area. We have calculated the time period. We have calculated the directivity. We have calculated the directivity in terms of the dB also. Okay, so many parameters we have calculated, few because we have simplified today on the basis of your radiation or electromagnetic radiations. So depending upon the expression, that is a derived expression, we can use that formulas and we can substitute the value and we can finally see what should be the radiation, okay, of your electromagnetic waves. For the every cases, the radiation will be different. We are interested to learn about that radiation in terms of your the electromagnetics, or by considering the antennas and all, while you are going to transmit, receiving anything at that time, how you can find the basic parameters related to that antenna or the radiation, that we have tried to simplify the numerical on that basis.